This is the third in our series of 3 stem cell podcast episodes from ISSCR 2020. This time we're talking with Dr. Martin Pera. Hey everybody. We are Daylon and Arun. Welcome back to the Stem Cell Podcast, where we culture knowledge in stem cell research by talking to some of the brightest minds in the field. Hey, everybody, just a quick note about today's recording of the interview with Dr. Martin Pera from the ISSCR 2020. We did have some sound issues there, some hiccups in the audio. We apologize. We know it's annoying. We hope it doesn't detract from your experience. This is the third in our series of 3 ISSCR 2020 episodes, so you all know by now that Arun and I attended that virtual meeting. It took place at the end of June. We're here today to talk to one of the researchers who presented at that meeting. But for those of you who weren't able to attend, you can catch up on everything you missed by watching the daily videos that we released throughout the conference, in which we summarize some of the hottest talks presented each day. To watch, visit stemcellpodcast.com/ISSCR 2020. Today, we have Dr. Martin Pera from the Jackson Laboratories on the podcast to discuss the research presented during ISSCR 2020. He talked about the unique properties of a subset of human pluripotent stem cells with high capacity for self-renewal. We're going to talk to him about that, but before we get there,
take your human pluripotent stem cell cultures further with mTeaser Plus from STEMCELL Technologies, the most widely published medium for feeder-free human ES and iPS cell maintenance is now formulated with enhanced performance and versatility. mTeaser Plus reduces medium acidosis for more stable cultures all weekend long. To learn more, visit www.stemcell.com/mTeaserPlus.
all right, guys. For episode 3 of the ISSCR 2020 interviews, we have with us Dr. Martin Pera, who's principal investigator at the Jackson Laboratories. Pera has 2 main areas of research using pluripotent stem cells. They look at extrinsic factors that regulate cell pluripotency and lineage specification during early human development. Also, interesting genetic factors that influence regeneration and repair in the central nervous system. Dr. Pera, thank you very much for joining us today.
Thank you. It's a pleasure.
So we'll get right into it, Dr. Pera. Both Daylon and I attended your ISSCR talk discussing your recent paper, which was focusing on a subset of human pluripotent stem cells with a high capacity for self-renewal. And this is something that's become a bit of a hot topic in our field, the idea that even in a theoretically homogeneous population of cells, there's more homogeneity or heterogeneity than we thought, right? So if all of our pluripotent stem cell cultures have these high self-renewal capacity cells as a subset, the natural next question is how can we harness them to actually improve the stability and differentiation potential of our cultures? So tell us a little bit more about these special cells in our cell cultures.
Sure. My lab got interested in heterogeneity in stem cells some years ago. And over the years, we've tried to dissect this using a range of different approaches, biological assays, metabolomics, transcriptomics, epigenetic approaches. And it's clear that the subset of self-renewing cells in human pluripotent stem cell cultures is a minority with some very special properties. And in our latest work, we tried to understand where that population mapped in terms of primate embryonic development. And it turns out it's closest to an early post-implantation state. But as I say, the population is a minority. And so what we're trying to do now is to explore whether we can stabilize that state more, because what you have at the moment is a very dynamic situation where cells are beginning to be lineage prime, beginning to head down a pathway towards differentiation, probably going through a lot of epigenetic change. And we think that things might be improved if we could further stabilize those cells at the top. So that's what we're working on now.
So, Dr. Pera, heterogeneity is du jour, and single-cell genomics has really elevated and illustrated the heterogeneity in these cultures. But I feel like we've been observing heterogeneity, and in some cases, I guess, ignoring it or kind of like sweeping it under the rug since the beginning. I mean, you were among the first to derive human pluripotent stem cells, and I think you would agree from the beginning. We could see in self-renewing conditions that there was a lot of heterogeneity just to look at it. So is there anything else like that we've been observing, something that's been right in front of us that you think deserves or needs closer attention moving forward, like the heterogeneity?
Yeah, I would say that another thing we tend to overlook is that I think even during routine passage with relatively gentle techniques, there's an awful lot of cell death going on. One of the most informative things we did in my lab was just to take some time-lapse images of cells immediately after passage. And you see some incredible things going on. You see colonies moving around, merging, colonies just going extinct. And so what I would say is in that early period, just after you subculture the cells, there's an enormous amount of attrition. And I don't think we understand that adequately either.
Yeah, so Dr. Pera, you're an expert when it comes to all things pluripotency and all things, stem cell culture. But I wanted to ask you about totipotency too. And this is, of course, a topic that was covered a little bit at the ISSCR, in particular by Janet Rossent, who has been hunting for totipotent stem cells that are equivalent to these 2C cells that exist after the first division of the zygote. And of course, totipotency means that these cells are going to have the ability to give rise to the somatic and extraembryonic tissues too. So the question I have is pretty. Do you think we'll ever actually be able to isolate and maintain these so-called totipotent stem cells? And what obstacles do we have to overcome before we can make that happen?
Well, that's really the kind of $64,000 question in the field at the moment. Mm-hmm. Can we stabilize totipotency? And there have been some very strong efforts, I'm sure most people will be aware of. But I don't think anyone has nailed it just yet. And the question is, mammalian development at the stage of the epiblast is clearly regulative. The cells can respond to different signals to do different things. It just depends on whether that very early state is something that can respond to external signals that will ultimately amplify it and keep it in one place. And I'm a little bit agnostic about that. I'm not sure whether that's possible or not. Certainly, people will, I suppose, continue to screen a lot of conditions and perhaps small molecules, et cetera, to see, using appropriate reporters, to see if this state can be captured. But we have to remember that there may be a lot of synthetic states that can be captured that may be a little bit different to what's really in the embryo. And I think Janet Rossant's point was really to say, well, we have to have pretty tough criteria to define such a cell, and let's be clear about what those criteria are.
Mm-hmm. So yeah, just staying on the note of totipotency, Mitanori Saito received the Momentum Award at this year's ISSCR, much deserved in my view, as I think he deserves a lot of the credit for making germ cell derivation a reality from pluripotent stem cells, something I think many assumed, at least I can speak for myself, I assumed it'd be on par with the challenge of hematopoietic stem cell generation, which we're still, not quite there yet, although exciting news at this year's meeting in that regard. But Mitanori was very cautious in his assessment of the clinical translation of that technology specifically. And I think it's for obvious reasons. We're talking about the germline here, and that deserves special attention and special scrutiny and extra care. But speaking to other less fraught cell types or tissues, do you think we're ready for prime time?
In what sense?
In sense that, do you think, it's been 20 years now, over 20 years, and I think that a lot of people predicted near applications. And I think now we're suddenly really on the precipice of it. But is it, maybe there was that same expectation 10 years ago, it all fizzled. Do you think that we're actually now really on the cusp? Or do you think that we need to really stall our enthusiasm and take care in the vein of Mitanori Saito's conservative view?
Well, I think Mitanori is dealing with a cell type that has some profound ethical issues associated with it in terms of any clinical application, to say nothing of the complexity of getting a cell safely through meiosis in a genetically intact fashion. With respect to some of the other applications, we've heard about many trials going on now. My own feeling about these trials, and I was very pleased to hear my former colleague Ben Rubinoff from Israel discussing their progress with macular degeneration. Other groups are making good progress in that area as well. My feeling is that many of these early stage trials probably won't lead to cures, and they'll probably raise as many questions as they answer concerning how stem cells, what they actually do, what their derivatives do when they're put into a pathological environment. And, to what extent they actually undertake functional replacement of missing cells. But to me, it's essential we're doing these clinical trials, because otherwise we're never going to find out where the gaps are and what we need to do next. So I'm very glad to see them proceeding ahead. I'm prepared. There will be adverse events. There will be setbacks. But these are steps we have to take if we're ultimately going to get to real cell replacement therapies.
So the translational side of things was, of course, a big emphasis at ISSCR, and as we mentioned, Dr. Saito received the award too at last week's ISSCR. And you're, of course, the editor-in-chief of the official journal of the ISSCR, which is Stem Cell Reports. And of course, over the years, there's been an explosion in the number of stem cell-centric journals, but Stem Cell Reports has remained pretty constant in terms of really quality, basic, and translational stem cell science. It's also open access, which is, of course, the wave of the future when it comes to scientific publishing. So as the editor-in-chief of Stem Cell Reports, what's your vision for the future of this pretty foundational journal in our field?
Well, of course, I inherited the journal from Christine Mummery, its founding editor, and I inherited a going concern, if you will. Christine did a great job in terms of and her colleagues did a great job in getting the journal off the ground. I think as we go forward, we really will see more applied and translational research. I'm hoping we're beginning to see that already. That can range from disease modeling and new approaches to drug screening, functional genomics, right through to clinical trials. But I think, as I indicated, whilst it's great to see these applications moving forward, we've still got an awful lot to know about the basic biology of stem cells and how they behave, and the basic biology of tissue repair and regeneration. So I think we'll continue to have a very strong effort to attract great basic science as well.
Yeah, Arun mentioned your role there, and we as scientists and, in society, we have the pleasure of straddling this kind of shift in science communication and publication. Your open access over there. There's also these preprint journals. I've heard some rumblings about there's this thing out there I heard about called Tweeter or something. I don't know. It's a real whirlwind. What's your level of adoption of all these various modalities? Is it like the proliferation and application of tech and science? You have to evolve or become extinct, or are you pretty traditional, old school in your communications?
I follow the preprint servers. I think they're a great place to see emerging information. If I see I recently learned how to tweet. The journal thought it would be a good idea if I did so. So we try and go out of our way when we see an exciting preprint to draw attention to it. So I think these things are really valuable. And I think they just help to heighten awareness of what's going on in a very rapidly changing field. So we keep an eye on all that stuff, and we try and keep up with it, though I have to say it is challenging.
Certainly challenging, but let's help Dr. Pera get his Twitter followers up. It's Martin Pera Jax for all of you tweeters out there. And shifting gears a little bit, Dr. Pera, you're at the Jackson Laboratories, which is evidenced by your Twitter handle. And the Jackson Labs, for most American biologists, is known as a place where all their mouse strains come from, right? But it's way, way more than that, and has such a storied history when it comes to human biomedical research and genetics. And actually, I was there on vacation, in Bar Harbor, Maine, with my wife a couple of years ago, and I made sure that we actually stopped by the Jackson Labs just to kind of soak in the aura, and also because I'm a huge nerd who visits laboratories on vacation. So you haven't been at the Jackson Labs for too long, but what drew you there, and what makes it such a special place scientifically in your eyes?
So the particular reason I came to the Jackson Lab was a few years ago when I was working at Melbourne University. A number of us were talking about an initiative around traumatic brain injuries. So speaking to a lot of neurologists, neurosurgeons, neuroscientists, they all tell you it's a common observation. If you look at two patients, similar age, similar health status, similar brain lesion, often you see that one achieves a better functional recovery than the other. And when I asked the experts about this, they said, well, we don't really know much about it, but we're very, very interested in it because we're beginning to appreciate how recovery varies and how important that is to patient outcome. So I got the idea, well, maybe I could use stem cells in a dish to model some of those recovery processes and understand some of the genetics behind it. But it also occurred to me that really there was only so far you could go with that. Ultimately, you'd need to go to whole animal models. And that's where, after conversations with Nadia Rosenthal, who became the scientific director of JAC, she was then one of my colleagues down in Melbourne, I decided to move the lab up here and have a go at looking into that precisely. So we are using a combination of in vitro human functional genetics, along with mouse embryonic stem cells, which I would say are a greatly underrated resource now. Those in combination, and then moving through to the in vivo situations. So that's a general idea of what we do here. The JAX now has a real emphasis on using its mouse models to understand human disease, to make the crossover between human genomics and mouse genomics, and to build better models. And they're also taking a big push to exploit cellular resources, in vitro resources as well. So it's kind of a great situation.
So, I mean, this may be a little bit redundant here because you did a good job at answering that question to completion, but it goes back to this idea of like the evolving role of the mouse. You said that mouse embryonic stem cells are vastly underrated as a resource, so I think that's part of what you're getting to in the answer to this question. But just to circle back, the first bone marrow of course you know this, the first bone marrow transplants in mammals were performed at Jackson Labs. So, arguably, this is the fertile ground from which the entire stem cell field has grown. But, like Arun said, it's also the world source for more than 8,000 strains of genetically defined mice, right? So you just answered how they're trying to incorporate the disease, understanding of disease in human in vitro and mouse in vivo and genetics, all this. But also, in part, do you think that your migration there as someone who has a strong emphasis in human embryonic stem cells, human pluripotent stem cells, either institutionally at Jackson or more broadly in the scientific community, is part of an expansion kind of beyond or transcending mice as the preeminent model for addressing human disease? And I say this because at the ISSCR, you saw as well as I that we're getting into all these compound, assembloid, organoid models where it seems like, it's no longer, there's a lot of benefits to looking at it in the physiological context of a living organism, but it seems like we're addressing questions that were beyond our imagination even a few years ago.
So I think the real future lies in exploiting both. And there's no question but that the in vitro models, and I've been an advocate of that from day one. I always saw that one of the biggest contributions of pluripotent stem cells would not be to transplantation medicine, but in their use as research tools for all of the things that we're doing now. That said, and I've been a proponent of that approach my entire career, I do recognize, as I think most people do, that powerful though these models will be, that they will never completely make an intact organism. And so what the JAX in particular is trying to do is to move away from the use of one strain, C57 black, genetics N of 1, to incorporating a lot of mouse genetic diversity into what it does. And thereby, there's already strong evidence coming from our lab and from others, and not my lab, but the Jackson lab and other labs, that shows that by using mouse genetic diversity, you arrive at better in vivo models of human conditions. And so that's another thing we're very excited about. And I think that it's very short-sighted indeed to assume that we're going to learn everything we need to know by looking at cell culture models or organoid models, powerful though they may be.
Well, certainly there's a lot left to be done when it comes to the basic biology of stem cell pluripotency, and perhaps some of these models are going to help us better understand that as well. And so thank you so much for joining us here today, Dr. Pera. And before we let you go, we're going to ask you a couple of science peripheral questions to kind of help our audience get to know you a little bit better. So starting off, what non-science book are you reading or that you've read that is really great and that you want to share with our listeners?
So just recently, I read a book called Killing Commendatori by Haruki Murakami, the great Japanese novelist. And I just love his work. He puts very ordinary people in ordinary situations, and suddenly they're going down very, very strange pathways. And it's fascinating. There's a lot of philosophy in it, a great storyteller. And on top of that, he's fascinated with cats and jazz, a couple interests of my own.
Yeah, you're not the first guest who's recommended that particular author. So I guess great minds are total maniac, insane scientists that think alike. It depends on how you classify yourself. The next one, last, we love this. I think, rare that a scientist is willing to put himself out there, but you can do whatever you want at this point in your career. Tell us, what was your greatest science blunder?
Okay, well, that's an embarrassing one. What I would say, and I say this quite seriously, when I was a group leader at the University of Oxford in the mid-90s, being relatively young and foolish, I built up a scientific portfolio that consisted solely of high-risk, high-payoff projects with binary outcomes. Binary meaning either you get the answer and it's fantastic, or you don't and you have nothing. And those two projects, the first one was trying to purify a growth factor that did for human cells what LIF does for the mouse. We had human teratocarcinomas that were feeder dependent. This factor substituted for the feeder layer. The second project was trying to isolate human pluripotent stem cells from either the blastocyst or fetal germ cells. Within the time frame of our grant there, we failed at both. And what it taught me was, and it's probably good advice for young people, definitely take these projects on, but make sure they're not the only thing in your portfolio.
Wow, that's a bit of wisdom there. Thank you for sharing. Forcing me to now reframe every single project I thought of, make sure I don't have binary outcomes. Yikes! But
it's fine to have a few of them, but have a few that are pretty, straightforward.
Yes, well, you gotta run the shop, right? But you're no stranger to risk, and I think you're an inspiration to our listeners. Someone it's nice to know that you've taken big risks, because some of your risks have paid off and in a careful way. So I've always admired you as a scientist, and I'm not alone. Thank you so much for sharing those insights with us today, Dr. Pera. We'll hope to have you back again sometime soon.
Thanks very much. It's been a pleasure talking to you.
All right, guys, that brings us to the end of our show. Don't forget to subscribe to our newsletter at www.stemcellpodcast.com to get a summary of previous episodes, also links to all the interview notes. You can also reach out to us on Twitter @StemCellPodcast or via email at info@stemcellpodcast.com with feedback or to suggest guests. Thank you so much for joining us for this episode. Be sure to check in with us in a week or two where we'll have more for you.